So, oh, I forgot. Today is the 23rd, I think. So you said 93 on 311, yes. Okay. So in 93, we're asked to find G comp F of 0. Before I even look, I have to write what this means. What does it mean? It means G of
X.
Yes, true.
Zero.
But since it's 0, I will put 0. But you're correct. So this is my starting point because this is the inner.
So I have a question.
Yes, please.
So for the G of F, that means you're putting F into G, right? If you're replacing the X's with F into
G of F means that I replace X in G by F.
Okay.
Because F is the inner.
Yeah.
Okay. So now we have to continue with G of 0. So let's look at F of 0. So F is in blue. F of 0 is? F is in blue. F of 0 is?
2, -2.
It's in blue. It's above the x-axis.
It's 2.
You see that too? It's right here. F of 2. F of 0 is 2. Not negative 2.
Wait.
F is in blue.
Yeah.
F is in blue. When x is 0, it's this. This is x equals 0. You draw a vertical line at 0. It crosses the graph of the blue function at 2. X equals 0 is this vertical line. It crosses the graph of the blue function when y is 2.
Okay.
So this is g of 2 now. So now I have to look at the purple function and determine g of 2. So here's the purple function right here. I imagine that I draw a vertical line at x equals 2, and I know it's almost outside of the graph, right? So it's at -6. So x equals 2, it crosses the graph in this point, and we read y equals -6. Is that okay? So the answer is -6. Is that okay? Better? Yes?
No.
Which part is
I'm
not?
just lost.
On?
How you the 2? When we're looking at 6 on the midterm in the test 2.
Is it clear how we got f of 0? So this is
Well, they
blue.
give you the blue.
Okay, so this is x equals 0.
Yes.
I read 2.
Okay.
So then g of 2 will be, I have to draw a vertical line at 2 now, and it crosses the purple function here, and I read -6.
Thank you.
Better?
Better.
Perfect.
So much better.
Awesome.
Thank you.
Anything else? Other questions?
Oh my goodness, I feel stupid.
That's okay. I'm going to be in your company, or you are going to be in my company. Okay, other questions here? Anything from anything? Anything from anything you want?
Yes.
Yes.
Ready?
Yes.
It's from this one's from the
Yes?
my lab.
Good.
It's F(x)
F of x.
equals 2 parentheses x minus 3 squared minus 3. It's the circle.
This is the parabola.
Yes, that is the problem. Oh, yes.
The circle has to have x and y in it. Okay, what are we trying to do?
Well, I think I got all the way down to where I couldn't figure it out at the very end.
But are we asked to graph it? Are we asked to?
We're asked to find the x and the y-intercepts.
Okay, so let's start with that. Okay, so how do we find the x-intercept for any function?
Let y equals 0.
Very good. So then I have 2, x minus 3 squared minus 3 equals 0. How do I proceed? Of course, so this is ready for which of the four methods of solving quadratic equations? Taking the square root. Awesome. So I will move 3 and divide by 2. It's a must. So move 3, divide by 2. And only now I take the square root. And I have to remember something very important. Because if I don't, I will only get one solution instead of 2. Correct. So then I have x minus 3 equals plus or minus the square root of 3/2. My math lab will ask you to rationalize this, I'm pretty sure. Or approximate it. What did they say? So let's move 3. Do they want the exact answer? Do they want the approximations? We will not be able to graph this. So they should be they should allow us an approximation.
So that's the zeros.
I'm sorry? These are the zeros.
So 3 plus.
Yes, yes. These are the zeros or the X-intercepts, correct. So they want approximations. How many digits?
Tens.
Okay, very good. So, yes?
Yeah, tens.
Okay, perfect. Let's do that. Perfect. So let's plug it in. So 3 plus the square root of 1.5 and 3 minus the square root of 1.5. So 3 plus the square root of 1.5. That's 3 over 2. And the other one with minus. Okay, so we got two solutions, 4.2. 4.2, so x equals 4.2 and 1.8. So these are the two solutions. So we have 4.2 comma 0 and 1.8 comma 0. These are the x-intercepts. How do we find the y-intercept for any function? So yes, perfect, perfect. So we have to determine this. So let's do this together. Because this is not that difficult. So 0 minus 3. Negative 3 squared. 9 times 2 minus 3. That's it. So the ordered pair is 0, 15. So we determine the x and y intercepts. What do they want next? Is this clear, everyone? Anything else? What else they want? The vertex. Can anyone identify the vertex? Yes? Very good, awesome. Right, we know that. So it's x squared, then x minus 3 to the left, then a vertical stretch, and then we go down 3. So obviously it's 3 comma negative 3. Perfect. Is the problem asking us anything else?
Well, I have written down fx is equal to a parentheses. That's the circumference, the circle.
That might be that must be a different problem because this is not a circle. Can you take a picture with your phone next time when you get on it?
Yes.
Okay, and
Yes, I will.
bring it to class?
Yeah.
Okay. Is there any, but is this clear, what we
Yes.
did so far? Okay. The axis of symmetry will be x equals 3. The minimum will be negative 3. And the range?
Negative 3. Infinity.
Good. Anything else? Yes, Amanda?
I don't have like an equation for it, but can we go over odd and evens, like just one problem?
From each?
Just one, like here.
You choose which degree and let's make it up.
Let's make it.
Even? Okay. Any preference for degree?
No, but how do you determine the degree? So it's like it's degree, like do you add them together?
Okay. So a to the nth power times a to the nth power, we copy the base and we add the exponents. So if I have x cubed times x squared times x to the 4th, what is the degree?
4.
10. Copy the base, add the exponents. It's the same rule. copy the base, add the exponents. Is that okay?
So if you add those up, if it's like an odd even number, that's gonna be really odd.
Exactly. Is this clear? Any questions? Yes or no?
What is this for?
Finding the degree. Yes. This is the rule, the exponential rule. Copy the base, add the exponents. 3 plus 2 plus 1 plus 4 is 10. That's how we determined the degree of this expression. Okay, so we want a degree of, you said even? Okay, any particular one? Is 4 okay?
Yeah.
Okay, so let's say negative x squared, x plus 1, x minus 3. What is the degree of this polynomial? Two times 1, right? X squared times x, copy the base, add the exponents, degree 2 plus degree 1 plus degree 1. Linear, quadratic. So when we multiply two linear factors and a quadratic, we get degree 4. Is that okay, everyone? Perfect. So what is the maximum possible number of turns? Very good. It cannot have more than 3. It doesn't have to have 3. Okay? Very good. We start with the domain. Very good, because it's a polynomial function, degree 4. Perfect. Okay, let's determine the x-intercepts. How do I determine the x-intercepts? Awesome. So I have negative x squared, x plus 1, x minus 3 equals 0. Very good. Yes, indeed. So I will just remind you that I would have normally multiplied both sides by negative 1 to eliminate that confusion that negative 1 could be something. Okay, so then, bless you, we expect 4 solutions. So again, I know you said them, but please forgive me if you said them. What? How many times? What is the multiplicity? Good. Next one. X equals, perfect, multiplicity. Good. And x equals multiplicity. Good. Multiplicity 2 plus multiplicity 1 plus multiplicity 1 is the degree 4. Yep. Perfect. So I put them in the table. I have in ascending order, be very careful. Negative 1 is first, 0, and then 3. So what does negative 1, 0 represent for this function? Awesome. What does 0, 0 represent for this function? Awesome. And what does 3, 0 represent for this function? Very good. Let's decide upon the end behavior. One more time, is the even degree or odd degree? Even, which means these are the only two possibilities. 1 or 2. Yes, because the leading coefficient is negative, which means that's all we need. The only thing that is not in the table, so you can say the y-intercept, but I already have it. When x is 0, y is 0. It cannot have more than one x-intercept, otherwise it's not a function. The only thing that doesn't fit here is the symmetry. Which will, absolutely. Here's why. If it crosses the x-axis at negative 1 and it crosses it at 3, there is no way this is symmetric with respect to the y-axis or with respect to the origin. There is no way. So I will just make a note, and I know that you know what you're talking about. I will say F is not symmetric. So you didn't forget. Okay, so let's graph. First, we will plot the ordered pairs. I only have negative 1, 0. I have 0, 0, and 3, 0. That's all I have. I'm only looking at the table. I don't care for any other work. So let's try to understand what this means. So you don't have to create more points and waste your time. So from negative infinity, it's coming up to cross at negative 1, 0. It has to turn because it comes back and turns at 0, 0. So it has to have a maximum, has to come back and turn at 0, 0. Then it has to come up to another maximum because it crosses at 3, 0 and going to negative infinity. One more time. From negative infinity, must cross at negative 1, 0, has to have a turn here because it comes back and turns at 0, 0. And then has to come up to another maximum because it comes back and crosses at 3, 0 going to negative infinity. And that's the graph. What we don't know is how high, how low. We don't care. We're going to determine that with the graphing calculator. So from negative infinity, it crosses at this point. It has to come to a maximum because it comes back and turns here, according to our calculations. It has to come to a maximum, again, because it comes back and crosses at 3, 0. Do I have any idea about how high this is? No. Do I have any idea about how high this is? Absolutely not. In algebra, we don't have enough tools to determine those max or min. I know that this is a local min. There is no question here that this is 0, 0, but I have no idea about those. And that's why we have to use the graphing calculator to determine those. So let's go back to the calculator in y equals, put in this function that we just created, and it was negative x squared. And then parentheses, x plus 1. And then parentheses, x minus 3. I don't want you to spend too much time on these graphs. This is really the minimum that I need, and I don't need more. It's up to you. So now, do I want to adjust the viewing window? I'll start with the standard, although I really don't care for the negative side. There is nothing to see there. So I could go to the viewing window and make those adjustments. So I see that negative 5 to 5 is good enough with a scale of 1. What did I do? Okay, got it. Okay. So I want negative 5 to positive 5. And with scale of 1, y minimum, I really don't care. Negative 3 is good enough. But I don't know how high for maximum. So I see it here. I'm cheating a little bit. I'm going to say 20 with a scale of 2 or 5. And I press enter. So as expected, and we knew that, it's crossing at negative 1, has to have a maximum. It has to turn. It comes back to turn at 0, 0. Comes up to a maximum because it comes back and crosses the x-axis again at 3, 0. Okay? So I can determine this maximum between negative 1 and 0, and this maximum between 0 and 3. With second and calc, I choose, is it frozen? No. Second and calc. Okay, so I want to find a maximum, which is 4. And I want it between negative 1 and 0. I don't want to guess, just give me the maximum. And I put it in the table or in the graph, negative 0.686, comma 0.54. So that's one maximum, and the other one is between 1 and 3. So second and calc, I want the maximum again, which is 4. From 0, enter, 3, enter. I don't want to guess. Just give me the maximum. It's at 2.18, comma 12.4 or 12.39. That's all I would like you to do with these functions. Just the x and y intercepts, find the max min, and graph them. So in order to complete the graph, I have to write f of x equals negative x squared, so I know what I graphed. So this is complete now. As we all see, is this function symmetric? No. You do not have to go back and adjust the graph. I don't care for that. Once you determine, obviously this is not a perfect graph, far from being perfect, right? This height is not 0.54, and this height is not 12. But I don't need you to make any adjustments. This is good enough. That's all we can really do with algebra. Okay, is there a next question? Is there anything else that you would like to go back to? Is there anything? Okay, so now I would like to continue with 3.5, which deals with rational functions.
Did we finish 3.3?
We didn't do synthetic division.
We did not do synthetic division? Sorry
We
then.
did move on. We did bond division. We didn't do synthetic.
Oh, yeah.
Okay, very good. Sorry. My apologies. Let's go back. Thank you for keeping me on the right track. Okay, so let's look at, let's start with an easy one like number 9. So on page 392, and which is 2x cubed plus 7x squared plus 9x minus 20 divided by x plus 3. And then I would like to look at 27 on the same page. Okay, so can I apply synthetic division on this?
Yeah.
But with synthetic division?
No.
Okay, that's fine. That's fine. We check the answer then. Awesome, awesome. Let's see, maybe we come up with something else now. No. I certainly hope not. Okay, so can I use synthetic division on this?
What's up there for a different one?
You need to.
We have to
Mess
make
with
sure, because remember, we cannot use synthetic division on everything we want. It's restricted to only when the denominator is a linear expression. Is this a linear expression? Or quadratic or cubic? Linear. So if it is linear and there is 1 as the leading coefficient, because otherwise we have manipulation to perform. So 1 is the leading coefficient, linear expression. The answer is yes. I can use, bless you, I can use synthetic division. Okay? Now I need to identify A. Remember, we know this from the circle and from other things. X minus A is this, by comparison. So can you tell me what is A? Perfect. Because -3 will go in this little box. So for synthetic division, I have to identify A. A goes into this little box. Now here's the next question. Is there any missing term from the top? No. Are they both in descending order? I should have asked that first.
Yes.
They have to be in descending order. And if there is a missing term from the top, we would have to write 0 for the coefficient of the missing term. But there is nothing missing. So now the next step will be I copy each and every coefficient. If there is one missing, I have to put 0. Degree is 3. Degree 3 is here. Degree 2 is here. Degree 1 is here. And degree 0 is here. Leave some room under these numbers and draw a horizontal line. So the algorithm for synthetic division requires us to copy the leading coefficient, no matter what it is. The leading coefficient gets copied. And then the syntax or the steps are the following. -3 times 2 and write the answer here. How much is -3 times 2? Good. So now please perform the operations you see. Correct. I continue in the same way. -3 times 1, I write the answer here. Perform the operations you see. Same step. -3 times 6. And I box this in. What does this mean? Exactly. That will be the remainder. Now here's a question for you. And this is also based on exponential rules. The degree of the top is? The degree of the bottom is?
1.
When I divide degree 3 by degree 1, what degree do I get? So this is the coefficient of x squared. This is the coefficient of x. That's the next in line, right? And this is the free term. That's how we read the answer. One more time. The degree of the top is, the degree of the bottom is. So when we divide degree 3 by degree 1, we get degree 2. So this will be 2 plus minus over. Awesome. So then the answer will be, and I hope we got the same thing last time. So 2x squared plus x plus 6 minus 38 over x plus 3. So this is the method called synthetic division.
How did you know it was 2x squared?
When we divide degree 3 by degree 1, what degree do we get? 2. So when I get degree 2, I have to start with x squared. Okay, here's another problem. Let's say 27. And you see in the next section we are going to use this.
Is this synthetic division or long division?
Synthetic. Long division is like the regular numerical division. It just looks differently because of x. So we have x to the 5th plus x to the 3rd minus 2 divided by x minus 1. So now let me ask you this. Is x plus 3 a divisor or a factor of the top? No, because there is a remainder. Good. Okay. So first of all, I ask myself, can I apply synthetic division here? Because that's the question. Yes. Are both in descending order?
Oh, yes.
Yes. Is there a missing term from the top? Okay. What is A? What goes in the box?
1.
Indeed. So now please dictate the first coefficient.
1.
The next coefficient.
0.
Awesome. The next coefficient.
1.
The next coefficient.
0.
The next coefficient.
0.
The last coefficient. That's it.
Where are all these zeros coming from?
Okay, degree 5, degree 4 is missing, degree 3, degree 2 is missing, degree 1 is missing, degree 0 is there. Better? Good. The procedure is identical. We have to copy the first coefficient. Please dictate the next step. 1 times 1. Good. Perform the operations you see. 1. So multiply 1 by 1. Perform the operations we see. 1 times 2. Perform the operations we see. 1 times 2. 0 plus 2. 1 times 2. Box in what?
0.
What do I conclude immediately about x minus 1? It must be a factor of the numerator because the remainder is 0. I divided degree 5 by degree 1. What degree do I get? So what is the answer? Please dictate the answer.
X to the 4 plus x to the 3rd, 2x squared, 2x plus 2.
Very good.
So that's the 50 disappears. Oh, because you divided it and now it's degree 4.
Right,
Got it.
right. Very good. I love it when my students answer their own questions. Less work for me. Any questions? So this is important to say that now I know that x minus 1 is a factor of x to the 5th plus x cubed minus 2.
Can you do one long division one?
Yes. Any preference?
No, I don't.
Okay, so let's divide this one. X to the 5th plus x to the 3rd minus 2. I had to leave space for x to the fourth because it's missing, for x squared because it's missing, for x because it's missing, and -2 is there, and so on and so forth. Okay. So x times what is x to the fifth? Perfect. X to the fourth times x is x to the fifth, and we have to change. Notice that here we did not have to do that. Here's why we did not have to do that. Because we already took care of this sign by replacing this by 1. So by simply replacing a by 1, we took care of changing the signs all the way. But here we have to change every time we write underneath. So x to the fourth times x is x to the fifth, opposite. X to the fourth times -1, opposite. Are you with me so far, everyone? Okay, these two go away. I bring down x to the fourth plus x to the third. Next question. At the top, we don't lie. Next question. X times what is x to the fourth? Sign? We do not lie at the top. Exactly. X to the third times x. Subtract. X to the third times -1 is negative x to the third, but I have to write positive x to the third. And I don't need to bring this down just yet. Are you surprised that I ran out of room? No. Good. Neither am I. Okay, so now, x times what is 2x cubed? Sign? 2x squared times x. It's 2x cubed, but I have to subtract. 2x squared times -1. It's -2x squared, but I have to subtract. These two go away, and I have 2x squared. Next question. X times what is 2x squared? Sign? 2x times x is 2x squared, but I have to subtract. 2x times -1 is -2x, but I have to write positive 2x. So finally 2x, and I finally bring down -2. Finally, x times what is 2x? Sign? Exactly. We don't lie at the top. 2 times x is 2x. I subtract. 2 times -2 is -2, but I have to subtract. So the remainder is 0, as expected, because x minus 1 is a factor of the numerator.
It's not in the test, right?
I'm sorry?
This isn't in the test.
No, it is.
Not this long, no. But I would like you to pay attention instead of doing your homework or whatever you're doing. Okay. So rational functions, 3.5. Do not get scared about this section. It is a little bit more involving, meaning the applications here are way more sophisticated than applications for quadratics. What the applications do, look at quadratics. We throw a ball up in there, and we have a trajectory that is a quadratic function. Not a big deal. The applications here are way more sophisticated. We're going to look at, your book presents two very interesting ones. One of them is we take a little candy, a little piece of sugar, and put it in our mouth and see what happens. And what function will follow that. The other application is a patient is treated with some medication and takes the medication, and what is the concentration of that medication in his or her bloodstream 5 minutes later, 10 minutes later, and so on and so forth. Way more sophisticated applications. These are not very simple functions. Okay, but please don't get scared. There are 3 types that we can look at, and If you bear with me like you always did, you're going to understand this very easily. Okay, so I split them in 3 categories: type 1, type 2, and type 3. Your book does not do that. The reason why I wanted to give them separate names is because when we talk about type 1, we know exactly what we mean. When we talk about type 2, we know exactly what we mean, and you'll understand in a minute. Okay? But don't tell type 1 to anybody because no one will understand what you're talking about. So here's an example of type 1. 2x plus 4 divided by x minus 3. Here's an example of type 2. F of x equals x divided by x squared minus 1. And here's an example of type 3. F of x equals x squared plus 3x plus 2 divided by x minus 1. How did I come up with this, and what does this mean? And how do we know which one is type 1 and why this is in type 1, why is this in type 3? Okay, so let's take a look at the first one. What would you say about this function? Obviously, it's a ratio of 2 polynomials. That's what a rational function is all about, a ratio of 2 polynomials. But what would you say about the top? What is the first thing you will notice? That the top has degree. And you will also notice that the bottom has degree 1. So as long as we have degree 1 over degree 1, it's type 1. What if we have degree 2 over degree 2? It's still type 1. What if we have degree 3 over degree 3? It's still type 1. So what is type 1, basically? Same degree over same degree. This is type 1. So at the top, degree n, and the bottom, degree n. That's type 1. It will be a very little difference between type 1 and type 2. This is totally different, the third one. Okay, what do you notice in the second one? Degree, yes, and the bottom degree 2. So anytime the degree of the bottom is bigger, no matter what, it can be by 1 unit bigger, by 10 units bigger, we don't care. So degree in the denominator bigger than degree in the numerator. Just write larger degree in the denominator. That's good enough. Larger degree in the denominator. What about the last one? What do you notice in the last one?
The numerator has a higher degree.
Yes, but exactly by how much? Because we cannot go beyond that in algebra. Exactly by 1. So I will write degree n, and the top is degree n plus 1. So let's start with type 1. But let's present a list of items here. Okay. To graph a rational function, here's a list. I'm going to list everything, but the order is not important. We don't have to present them in this particular order. So here it is. 1, domain. 2, vertical. We have never discussed this. I'm going to start with what is new. Vertical asymptotes. Vertical asymptotes. 3, behavior of the function near the vertical asymptotes. I'm going to start with 2 and 3 because this is new. 4, X-Intercepts and what? And there, if that's the case, there, we know this from, thank you. It may happen or not. 5, Y-Intercept. So let's stop for a moment and go back, and the list continues. So domain, vertical asymptotes, behavior of the function near the vertical asymptotes. Of course, X-Intercept and their multiplicities, and Y-Intercept. Number 6, type 1 and 2 have horizontal asymptote. Type 3 does not. Type 3 has slant asymptote. Seven, end behavior. 8, max min with TI-84, if that's the case.
With T what?
TI, Texas Instrument,
Oh,
calculator, TI-84. 9, symmetry. 10, range. That's about it. I'm going to start with the two items that we have never heard before. This is one item because they go together, and basically this is another item. We know what this means, but not in the context of a rational function. So I'm going to start with these two, and then look at problems. As you remember, the first problem will take 10 minutes. The rest, the subsequent problems, will take 2, right? So it's a long time. It takes me a long time to explain. Okay. We looked at rational equations before. And we said restrictions on x, right? And we said x cannot be this and x cannot be that, correct? Because the function is undefined at that point. What does that mean? It means that the function has a vertical line that will never cross. And then the function behavior will be either approaching, as it gets closer and closer to this number, x equals 5, the function values will go to infinity or negative infinity, not both, because it will not be a function. And on this side, the function values go to infinity or negative infinity, not both, because it will not be a function. This line is called a vertical asymptote. So let me just give you a simple example. So if we say f of x equals 1 over x minus 2, we know that x cannot be 2. Here's what happens at that point. The vertical asymptote, x equals 2, is a VA. So we write x equals 2. It's a vertical asymptote. And now I don't know, in a minute we'll verify, I don't know whether the function will do this or this, not both. And on this side, this or this, not both. So whenever a function, a rational function, is undefined, the function will have a vertical asymptote unless, of course, there is an unless, and I'll show you the example. So just keep in mind there is one exception, and I will get to that. So if a function is undefined at the value of x, unless that special case happens, it will have a vertical asymptote, and the behavior of the function near the vertical asymptote is basically infinity from the left, or infinity from the left, or infinity from the right, or negative infinity from the left and negative from the right, or any combination. There are four possibilities. Infinities on both sides, negative infinity on both sides of the asymptote, or this, or this. And we will verify that for any rational function. Okay. So now the other new piece of information that we have never seen before is this. When we talked about polynomial functions, even degree, what is the end behavior if the leading coefficient is positive? Right? If the leading coefficient is negative. Now, if the degree is odd. But what happens with these two, the top ones, type 1 and type 2? They eventually approach a number, and that number is called horizontal asymptote. So these rational functions don't do this. They do this. So eventually they approach a number this way and the number this way. And that line is a horizontal asymptote. And we will be able to determine that. What happens to type 3? Type 3 does not have a horizontal asymptote, but it will have an asymptote that looks like this. It will be a line. That's why the difference. If the degree is 5 and 4, what is the degree of the ratio? Degree 5, degree 4, 1. That's why it's going to be a line. That's why it's required the top to have exactly 1 degree higher than the bottom. So then the quotient is a line. This problem, with the slant asymptote, I will put it as an extra credit. I will not ask you to do it. It's a little bit behind the scope of the course, in my opinion. Don't tell anybody. That just recorded it. So, but I truly believe I will put it as a problem to choose from. Is it difficult? No. But I think it's beyond the course of the beyond the scope of the course. Okay, so let's start with a type 1. So f of x equals 2x plus 4 over x minus 1. Like before, I am going to use the same table to summarize all the information so we have it all in one place, so we can easily graph this. Okay, so first I will prep the function a little bit and say, oh, I see that I could factor out a 2 at the top. There is nothing else I can do here. Then I will get my chart going, my table going, where I summarize all this information. Everything I find, I put in the table. Everything I discover about this function, immediately put in the table. So, of course, I have to start with the domain. What is the domain of this function? Except 1. So negative infinity, always remember 0 must be in the table no matter what. 1 and infinity. Look what I do. Clear? Why did I put this? Exactly. So since x minus 1, now I'm prepping you for that exception. Since x minus 1 cannot be simplified with a factor of x minus 1 from the top. Is there a factor of x minus 1 at the top that I can? No. That will always stay as a vertical asymptote. So right here underneath, I will write x equals 1 is a VA. Once I establish that that is a vertical asymptote, I will immediately write left and right infinity. This is not entirely correct, because I have not determined the sign of those infinities. I don't know if this is positive, negative, or negative, negative, or positive, positive, or negative, positive. I don't know that yet. Bless you. So I'm going to look at 1, close to 1, left and right. I will use 2 numbers that I will not plot, just to check. I'm going to use 0.9, close to 1 from the left, and 1.1, close to 1 from the right. When I plug in 0.1 here, just give me the sign. Don't calculate anything. I only want the sign of this expression when I replace x by 0.9. Perfect. I have to replace in the denominator as well. 0.9 minus 1, just the sign. So 0.9 minus 1, perfect. Positive over negative, done. I'm replacing 1.1 now. What is the sign of the top when I replace x by 1.1? What do I get in the denominator when I replace x by 1.1? So what will be the sign on the right-hand side of this asymptote? Awesome. Great. So again, what did I do? I established that x equals 1 is a vertical asymptote, and I used 2 numbers as close as I could, left and right, just to check the sign. I knew that these have to be infinities, but I didn't know if it's this, 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 or this. By checking with numbers very close, left and right, I only needed the sign. Perfect. So now, this is type 1. And type 1 has y equals leading coefficient over the leading coefficient, horizontal asymptote. Can anyone give us the leading coefficient of the top? Can anyone give us the leading coefficient of the bottom? So what is the horizontal asymptote of this one? 2/1 is 2. So 2 is the end behavior. And I make myself a note in the table. Y = 2 must be the horizontal asymptote. This is true for any type 1. As long as the degree of the top and the degree of the bottom are the same, the horizontal asymptote will always be the ratio of the two leading coefficients. Always remember, you have to have everything in descending order. If top and bottom are not in descending order, you will not determine the correct coefficients. Always keep everything in descending order. Okay, now we want the x-intercept. How do I determine the x-intercept for any function? Very good. So let's look at the original function and write 2 or this or the factor form equals 0 or 0/1 to trigger your memory. So there are two options here, right? I can say this is a proportion, let's cross multiply, or I can think and say, when is a fraction 0? Only when the top is 0. Because if the bottom is 0, the function is undefined. So when is the top 0? Okay, we don't know, that's fine. 2 times x plus 2 equals 0, x equals -2. So -2, 0. Careful where you plug it in. So it's -2 is between -infinity and 0. Now I have to plug in 0 to find the what? When I plug in 0 for x, what do I find? The Y-intercept. Awesome. So let's take a look back to the original. I covered what I didn't need. So when x is 0, how much is y?
4.
But it's 4 at the top and correct. So it's -4. Done. Okay, so let's make sense of the information first before we graph. So it's coming from 2. It will cross the x-axis at -2, 0. It will cross the y-axis at 0, -4, and go towards -infinity on the left-hand side of the vertical asymptote. That's what I see here. So from 2, crossing the x-axis, crossing the y-axis, and going to -infinity on the left-hand side of the vertical asymptote. On the other side of the asymptote, it's coming from positive infinity and approaching 2. One more time. So from 2, crossing the x-axis, crossing the y-axis, going to -infinity. On the other side of the asymptote, from positive infinity, going to 2. That's the graph. We don't have anything else. So let's graph. When we graph a function with asymptotes, we must graph the asymptotes first. Like we did with the quadratic function, no relation. But we graph the vertex and then the axis of symmetry. The same thing here. Although, bless you, although they are not part of the graph, I have to graph them first. So x = 1 is this. That's the first asymptote. And y = 2 is this. Y = 2. The next step, I have to plot the points I have. I have -2, 0, and 0, -4. So -2, 0. 0, -4. And then again, I look at my table. From approaching 2, crossing at -2, 0, crossing at 0, -4, and approaching -infinity on the left-hand side of the vertical asymptote. Then on the other side, clear from positive infinity, approaching 2. And that's it. Now we know how to graph rational functions. As you see, it's more involving. than a rational function, than a polynomial function that is continuous, smooth, whatever. We didn't have any gaps, any asymptotes, but we did have end behavior. With a graphing calculator, however, you have to be very careful, because if you omit to put parentheses around the top and the bottom, you will not get the correct graph. So parentheses, 2x plus 4, close the parenthesis, divided by x minus 1. There is one other function that I have to put in because the calculator is not smart enough. What is the second function that I need to put in because the calculator will not graph it?
Y equals 2.
Excellent. Thank you. Awesome. Good. So now let's think about the viewing window. We already graphed the function. Maybe the standard viewing window is good enough. So I'm going to go back to zoom 6. Let's see. It's crossing at -2, crossing at -4. It's coming from positive infinity, going to 2, and that's the horizontal asymptote. I don't know how to put the vertical asymptote in this software, so forgive me. There should be a vertical asymptote there. I haven't been able to figure out how to put it in. And that's the rational function. Can anyone give us the range of this function? Union? 2 to infinity. Very good. So range, -infinity to 2, union 2 to infinity. But if I put a bracket, the function is defined at that point. There is an x value that makes y equals 2, but there isn't one. Is that clear? It's like the range, like the domain. Domain is -infinity to 1, parenthesis, union 1, parenthesis, to infinity, because 1 is not there. What is the difference between type 1 and type 2? Just a tiny, tiny difference. The horizontal asymptote for type 2 is always 0. Why? Because the denominator is so much more powerful than the numerator. It's like, let's say we have a cake and we want to share it with everyone coast to coast. How much will you get? Too small to mention. So that's the only difference. So let's look at type 2. Same type of function. So let's say f of x equals x minus 1 over, let me make it plus, over, I'm going to make one up, and with that exception, x squared plus 3x plus 2. Okay. This is a rational function. It's a ratio of 2 polynomials. Is it type 1? It's not type 1 because it doesn't have same degree and same degree. Obviously, it's type 2. More powerful, bigger degree in the denominator. So it is type 2. Yes?
Oh, no. Type 3 just has that.
Type 3 is higher than the numerator. Yeah, type 3 is more sophisticated a little bit. Okay, type 2. So what would you do first, right away? Yes, but before domain, if I don't factor it, I will not know how to find the domain, right? So please factor the denominators we did last time with the numerator. Good. So I have to write how many restrictions? Perfect. And they are? Yes? Correct. Perfect. Awesome. Now let's look at